Whew. Is that you, Antonio?
No, it's Emily. Emily, kind of bad, no cap.
We'll get started in 2 minutes. So some of you have heard of a generating function before? Or none of you have ever heard of a generating function before?
No, I didn't really look at this stuff.
It's all right. Generating functions, most people don't learn about them in high school, not really. But you learn all the techniques that you need in order to do them. And they're pretty useful on a lot of different problems. So basically, I'm preparing like maybe 6 to 8 hours worth of information on generating functions and how they appear in counting, calculus, and number theory, and maybe a little bit of algebra. And Sam and I are collaborating on problems to ask you regarding these things. So today is just going to be kind of an introduction to some basic generating functions and some concepts from calculus as well. Has everyone here at least taken their first calculus class or is taking their first calculus class?
Yeah, I'm taking my first calculus class this year.
Has anyone not taken a calculus class? Okay. The most complex thing that we're going to be doing in calculus is taking the derivative of a polynomial. So nothing really that complex, but it's probably not going to look like the calculus that you do in your class. We're going to be using it for completely different stuff. For some reason, the derivative tells you something about counting. So we're going to see that as we go along. So I'm just going to start reading the notes. You can download a copy of this from the Discord if you want. And all the problems are also in the notes. So anyone who has done casework can tell you it's tedious. There's a lot of casework problems that we could come up with that really just wouldn't be feasible for us to solve by hand. Fortunately, the basic operations of arithmetic, addition, multiplication, subtraction, and division actually have the ability to handle all of the interpretive details for us. and we can just do routine computations in order to solve casework problems. Okay, great. You took Calc BC, then Calc BC is way more than we're gonna need, even though we're gonna develop some Calc BC concepts. Okay, so I want to open up with an example first that relates to stuff that you have probably seen before already. Most people have already seen this identity, I'm willing to bet. So I'm going to switch to OneNote, but again, you can, if you want to follow along in the notes, go ahead and download it from Discord. So let's see. Everyone knows that if we just have 1 plus q squared, and I shouldn't say everyone knows. Who hasn't seen this identity before? Everyone's familiar with this geometric series identity? I mean, we're here taking Amy level questions, so I assume so. If the absolute value of q, being q a complex number, is less than or equal to 1, sorry, it has to be strictly less than 1, so that is already a mistake that I found in my notes. If the absolute value of q is less than 1, then we can let this, then n can go to infinity, and we can say that 1 plus q squared plus dot 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 is equal to 1 over 1 minus q. So basically this thing goes away and then the minus signs flip this. This identity is really powerful. We're going to basically be looking at the consequences of this identity all day. So let's stretch it out. Okay, so let's take powers of this. 1 minus q to the kth power. Okay, so this is going to be equal to, or let's just do squared first. Let's see if we can find this. So probably a bunch of people have done this one before, but can someone simplify this expression for me? Let's see. Does anyone know what the pattern is when we do this multiplication? Here, maybe I will expand these out so that the pattern is easier to see. Okay, how many ways are there to get a 1, a constant term? There's just a single way, right? 1 times 1. Yep. And how many ways there to get a q? And how many ways are there to get a q squared? Yeah. So we can see the pattern here. Okay, there's actually 2 different ways that we can identify what this pattern is. There's a very simple way, and then there's like a more calculus way. Let's put the calculus way aside for just a moment. And can someone tell me what the pattern is? Yeah, it's just the natural numbers, okay? So what if we do this again? Cubed. So we have 1 plus q squared plus q cubed plus dot 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 plus 1 plus 2q plus 3q squared plus 4q cubed plus dot 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 dot. Okay, so what's the constant term going to be? Yeah, 1. And what's the linear term going to be? Yep, 3q, and then the quadratic term. This one's still not bad. Are you guys going to make Frank and Sam do all of it? So not 5. So we have 1 times 3q squared plus q times 2q plus q squared times 1. So that's 3q squared plus 2q squared plus q squared is equal to 6q squared. Okay. Now how about q cubed? How many ways are there getting a q cubed? There are 10 ways. That's right. So who's seen the pattern? What are these numbers? What is this sequence of coefficients? Yeah, these are the triangular numbers. That's right. All right. So then we could do one more. Do you want to do this one before we go to the general case, or do you want to just jump straight ahead to this one? To the kth power. Just go to the general. Okay. All right. So here's how we should be thinking about these. We have 1 plus q squared plus dot, 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 dot. And then we're multiplying a bunch of these together. Okay, so we're going to be summing, and now I'm going to use this sort of sum convention where it means this is the same thing as sum from n equals 0 to infinity. We're just summing on all natural, all non-negative integers. Sorry. Okay, so that is going to be our degree. Okay, so now we just need to figure out what is the coefficient going to be. Well, basically, we're going to get an exponent, let's say E1 for Q from this factor. And you know what? Let's actually move this over a little bit. So we have 1 plus Q squared plus dot, 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 dot. Okay, and then from this one, we're going to get an exponent of E2. And then from the last one, we're going to get an exponent of EK. So we're going to want to choose our exponents so that the sum is n, because we're collecting these together in n. So there's one unique way of picking an exponent for each of these, for each solution to the equation E1, E2 plus dot, 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 EK equals n, where the EIs are less than or equal to 0 and less than infinity. So yeah, they're non-negative. So we're looking for the number of possible solutions of this thing. So each solution of that equation contributes 1 q to the n. Does that make sense so far? This isn't our final step, but just this intermediate sense makes sense to people. Anyone confused? Kind of lost. Okay, so one way of thinking about the so basically let me do another step, an intermediate step. Come on, why is my pen not working? Sorry, I think my pen just died. Let me plug it in real quick. I haven't used this thing in so long. So we have to think about this kind of like the binomial theorem, except we have an infinite amount of exponents to pick from each parentheses. We have a finite amount of parentheses, but inside we have an infinite amount of terms. So let's just say this is the sum where E1 is greater than or equal to 0, E2 is greater than or equal to, greater than or equal to 0, all the way to EK is greater than or equal to 0 of Q to the E1 plus dot 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 plus EK. So what am I saying here? Basically, this is really ugly. This is going to be our final step, but basically, so for E1 equaling 0, we're basically picking this one right here. So this is E1 equals 0, and then let's say for E2 equal to 2, we're picking this one right here. And then for, let's say, EK equal to 1, we're picking this one right here. And what we're ending up with is Q to the sum of the E's. So does this step at least make sense? How we can write it this way? Okay. So the thing about this is we have k sigmas here for our sum notation. That's super ugly. We can get it down to 2 sigmas if we collect terms of like terms, right? So that's what this step is going to be here. Collect terms of Q to the n. So this is equal to the sum. Now on non-negative ends. So now we're looking for all of the ways that we can pick our exponents to add up to some number n. And each solution to this equation where our EIs are non-negative contributes exactly 1 to the coefficient. Does it make sense now? Oh, capital yeah. Capital yeah. I mean, we can keep talking about this, but we're almost at the finish line at the same time. This is the key step that explains where the pattern is coming from. So if each solution to this equation, each integer, non-negative integer solution to this equation contributes exactly 1 to the coefficient, then we're interested in asking how many solutions are there to this equation. So this is an important question we're going to come back to, but how many solutions to E1 plus E2 plus dot 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 plus EK equals n are there where EI is greater than or equal to 0 for I equaling to 1 to K. Okay, so this is a pretty standard counting question. Who knows how to answer this kind of question? Has anyone ever heard of stars and bars? All right. So what's the reasoning behind stars and bars? How do we apply stars and bars to this situation? You mean k minus 1 spots? Or so we're putting k minus 1 dividers between n things to split them up? Yeah. Okay, so no problem, Antonio. So stars and bars tells us that there is n plus k minus 1 choose k minus 1 solutions to this. So what we get is that 1 over 1 minus k to the, 1 over 1 minus q to the kth power is equal to the sum over the non-negative integers of n plus k minus 1, choose k minus 1 times q to the n. Okay, so this is our first, and this is a very important identity that we're going to be using for the rest of this introduction section. So is there any confusion about how we arrived at this this statement? Does anyone want me to go back over a certain step? Okay, so basically the big idea, the key idea is that this symbol is equal to this one. And we got that by thinking about partitions of n things. Okay, so we're gonna need this identity though. So let's go back to my notes and let's see what we're doing next with this. So we've obtained this identity right here. We want to get a combinatorial identity by finding the coefficient of q to the n in this expression using a different method. So we're going to rewrite 1 minus q to the negative kth power as 1 minus q to the negative k plus 1 times 1 minus q to the negative 1. So the negative 1 and the 1 cancel out. Okay, so this is, we just have this product right here, as you would expect. But we need to be able to multiply infinite series in general. So this is a great place to develop this identity. I do it in my notes right here, but I kind of just do every step automatically. So let's go through the intuition of why this should be true. So if I have, like, let's say a of q is equal to a0 plus a1q plus a2q squared plus a3q cubed plus dot dot dot. It's for some any complex numbers, or they could be real numbers, I guess. But any coefficients, and let's say we also have b of q is equal to b0 plus b1q plus b2q squared plus b3q cubed plus dot 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 dot. Okay, so what are the coefficients of AQ, BQ? Right, it's something plus something Q plus something Q squared plus dot 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 dot. Okay, so it's really easy to see what those coefficients should be if you write it out like this. A0 and then A1Q, A2Q squared, A3Q cubed, and then B0, B1Q, B2Q squared, B3Q cubed. So right here, we're going to have A0, B0 multiplying, and then A1B0 Q, and then A2B0 Q squared, A3B0 Q cubed. And you guys can see where this is going. I'm just going to fill this out while I'm talking a little bit. Because one thing that you should notice is that all of these diagonals right here actually end up having the same degree. So for instance, this should be A0, B2Q squared. So these are all the quadratic ones, right? Okay, can someone tell me a pattern that they notice about these terms on these diagonals? So that should be partially to kill time while I'm writing all this down. You can see the patterns that I'm looking for. No one can see anything interesting about the relationship between the coefficients and the degrees? Let's look at this term right here. I'll rewrite it again. A2B1 q cubed. Don't we have 2 plus 1 equals 3? I mean, yeah. Or for instance, if we take this diagonal right here, and we look at this term, a1b3 q to the 4th. Don't we have 1 plus 3 equals 4? I mean, technically, we also have, it's like a binomial expansion thing, right? Yo, 1 plus 4, that's crazy. Yeah, yeah. So it should be a4, b0, q5. So basically, what I'm trying to say is if we have a of q, b of q is equal to this sum n greater than or equal to 0, an qn times this sum n greater than or equal to 0, bn qn. What we should be getting is a sum, if we collect in terms of n, where we're looking for all solutions to this equation, I plus j equals n of ai bj q to the n. So we're trying to sum over all of these solutions, or all of the ways to split up n into two pieces. It kind of looks like what we were doing up here when we were doing stars and bars. This is all of the ways to split up n into k pieces. Just, you know, something to keep in mind. So typically we like to rewrite this in a less symmetric way, but in a more algorithmically easy way to just not think. So k equals 0 to n of a n minus k, bk, q to the n. But yeah, it's like the binomial thing. So we have this identity now, and so we can rewrite our 1 minus q to the minus k as 1 minus q to the minus k plus 1 times 1 minus q to the minus 1. So that's equal to sum over the non-negative integers of q to the n. Sorry, I'm going to do this in the other order, so that you have minus 1 here, minus k plus 1 equal to 0. Okay, so this should be n minus k minus 2. It's a minus 2 because we went down by 1 in k, so this should be k minus 2 here. Oh, and then we should also have the q to the n. I forgot to write that. All right, so everyone with me on just this step right here? Just making sure. Okay, all right. So now let's use this identity. Okay, so what this identity says is this is going to be equal to the sum on non-negative integers of the sum on k equals 0 to n of, so the coefficient of this is 1. So we have 1 times, we can do n minus k minus 2, k minus 2. And I don't have to change this binomial coefficient because this thing is technically symmetric. We could also write it, sorry, this way. We could put a k here and then b n minus k. It doesn't change it. So I think technically actually put the n minus k here. But since all of the coefficients of this one are 1 in the example that we're looking at, it doesn't really matter. And this is saying don't change the coefficient. All right. So, oh, I'm making the same mistake I made in my notes. This has to be an I. We need a new index here. So actually, we do want a minus I and a minus I. There we go. I almost made a mistake that I made before. Okay, because remember this K, let's remember what these variables mean for a second. So N is the degree of Q. K is the degree of 1 over 1 minus Q. Now I is this index that's appearing inside of this nested sum coming from this multiplication of these two series that we just did.
Wait, isn't there supposed to be an n plus k minus 2 minus I?
Yeah, it should be plus n. That should be plus n. Yep. But that is what we got up here from stars and bars. I just wrote it incorrect. Okay. So, what about this step? Everyone with me on this step? Okay. All right. So, I'm just going to clean this up because multiplying by 1 isn't changing anything. 0 to n. So we have n plus k minus 2 minus I, k minus 2 minus I, q to the n. And let me just remind you that we had before that this was equal to the sum over all non-negative integers of n plus k minus 1, k minus 1, q to the n. So just by comparing coefficients, we can then say that the sum from I equals 0 to n of n plus k minus 2 minus I, choose k minus 2 minus I, is equal to n plus k minus 1, choose k minus 1. Now, you might be saying to yourself, all right, Corbin, who cares? This thing is ugly. It's hard to remember. When am I ever going to use something like this? So I acknowledge that that is a valid thing, a valid response. So let's make this easier to look at and easier to remember. So let's say that m equals n plus k minus 2 and s equals k minus 2. Then our identity becomes sum from I equals 0 to m minus s of m minus I choose s minus I is equal to m plus 1 choose s plus 1. But that also can be a little bit annoying to look at. So we can shift our identity and rewrite it this way. And this is what I want you to memorize and also think of moving forward as the hockey stick lemma. So this is what we have right here. Hockey stick lemma. So you guys have probably seen that before, but did anyone have it memorized off the top of their head? Or what does this expression mean? What is this telling us? It's got something to do with Pascal's triangle, so I might as well start writing one. Can someone annotate over my Pascal's triangle what this identity is saying? Let's pick m is equal to 5 and s is equal to 2. Oh, that should be a 6. I couldn't add for a second. 6, 4, 1, and then 1, 5, 10, 10, 5, 1. So if we plug,
Isn't that just supposed to be I choose s in the sum?
Oh yeah, it should be I choose s because we went up. Yep. We got it. Okay. So I gotta fix that in my notes as well. Oh, sorry. I choose S. So what this sum is, according to these conditions, is going to be 2 choose 2 plus 3 choose 2 plus 4 choose 2 plus 5 choose 2 is equal to 6 choose 3. Well, let's see if that's true. 2 choose 2 is 1 plus 3 plus 6 plus 10. Wait, so I need one more row actually. Turns out. 1, 6, 20, sorry, 15, 20, 15, 6, 1. Is it true that 1 plus 3 plus 6 plus 10 adds up? Oh yeah, Antonio said it. Yep, it adds up to 20. All right, so you might be saying, Corbin, I already knew how to prove this using counting arguments. Or you might not be saying that, which is good because that's our first problem. I want someone to give me a counting proof of the hockey stick lemma. But the reason that I started out with this is because this is an example of how generating functions gave us this counting identity just by knowing how to multiply power series. We didn't have to think about what is the combinatorial meaning of this identity right here.
Wait, one thing to note, the picture you drew motivates why it's called the hockey stick lemma.
Yeah. Yeah.
Like it looks like a hockey, yeah, just for people to know.
All right, so I guess I better fix this in my notes. 1 second. But think of a counting proof. I want to hear a counting proof from someone. What are these sides counting? Let's see. Here we go. All right, recompile. I'll upload the fixed version to the Discord at the end of this. But exercise 1, use a counting argument to prove the hockey stick lemma. What are both sides counting? There's an algebraic argument you could do as well. I guess I would also accept an algebraic argument if someone wanted to prove it for me that way. Here's a challenge problem. This is, no one told me this one. I found it out just by, trying something, but I think that you guys are capable of doing this pretty quickly. So use a hockey stick lemma to prove the Pascal rectangle sum identity. The sum from I equals R to M of the sum from J equals S to N of I plus J choose I is equal to M plus N plus 2 choose N plus 1 minus R plus N plus 1 choose R minus M plus S plus 1 choose S plus R plus S choose R. Have you seen this one before, Sam?
Not exactly, but I can see how to prove it.
Okay. Should I wait for people to try to come up with proofs for me, or should I assign the homework for you guys to show me how to do it when we get back. See. Either is fine for me too. Let's see. Because exercise 2 might take a little bit of work to do, but if you want to do it next time, that's fine. If you want to submit your work to me, that's also good. But I want you guys to try at least, maybe sketch them out loud or, you know, whatever. But otherwise, let's keep going with our notes. So one identity that we just got is A of Q times B of Q is equal to the sum over non-negative integers n over the sum from k equals 0 to n of a n minus k bk q to the n. So this coefficient, I'm going to call that C sub n, is really important. We say that C sub n is the convolution, let's spell that right, convolution of the sequences an where n is greater than or equal to 0 and bn where n is greater than or equal to 0. So even though we got this just from multiplying two series, it has a lot of combinatorial significance, and so we're going to want to have a name for it. Exercise 3, I want someone to try to explain this for me. So now a little bit of notation, actually, I should say. I'm going to say that this symbol is the set of numbers 1, 2, to n. Okay. So I want you guys to prove that this product of I equals 1 to n of oh, it's actually stated wrong in the notes. Okay, it's fine. So the product of 1 plus x sub I from I equals 1 to n is equal to the sum over, so this is the sum over all the subsets of this set n of the product over all of the i's in the subset P of xi. So let me show you what this means for, let's say, n equals 3. For n equals 3, what we have is 1 plus x1 times 1 plus x2 times 1 plus x3 is equal to, now I'm just gonna fill in, I'm gonna skip all of the work, but I'll leave it up to you to check that you get what I'm about to write down from this when n equals 3. So you get 1 plus x1 plus x2 plus x3 plus x1 x2 plus x2 x3 plus x3 x1 plus x1 x2 x3. All right. So who thinks they can prove this for me? All right, so Sam did exercise 2. It's not that bad. It's pretty straightforward using the hockey stick lemma, but
Yeah, you just just use the hockey stick lemma a few times.
yeah, it's like 3 applications of the hockey stick lemma or something like that. So or maybe I'll leave this one. But there's counting arguments for this. I want you to think about it in a combinatorial way. So maybe I'll ask you guys to submit solutions to these to me on Discord or something like that. Anyway, let me show you exercise 4. Exercise 4 is also a pretty good one that I want people to attempt, or at least tell me if they're going to try to attempt it today. So exercise 4, this is called a Vandermonde convolution. And that says that m plus n choose k is equal to the sum from I equals 0 to k of m choose I times n choose k minus I. I want someone to try to prove this one to me using there's 2 different methods. So there's I will do the second one by using the binomial theorem. But the first one, I want someone to try to prove it by counting. Well, I don't know. Do I want to do one of the methods? Both of them are important. I do want to see the second method in class, but I almost want to make someone else try to attempt it for me, someone who's not Sam.
I mean, it's a good application of the stuff you were doing before. So
Yeah,
maybe someone can try.
it's a good one to try. There's 2 different proofs of this one.
Yeah, I'm talking about the algebraic proof.
Yeah. So I'll start the proof, but let's see if someone can at least fill in some details for me. So on one hand, we have x plus y to the power of m plus n is equal to the sum from k equals 0 to m plus n of m plus n choose k times x to the m plus n minus k times y to the k.
Yeah, I mean, x and y are interchangeable.
Yeah. Oh, should I do it the other way around?
It doesn't matter. It'll give the same result either way.
Yeah. Okay. On the other hand, we can write this as x plus y to the m times x plus y to the n. All right. Who can keep going? None of you guys know the binomial theorem? You can't tell me what the next step is?
Actually, honestly, it might be less confusing to use one variable.
Just do 1 plus
Like
x?
x plus, yeah, 1 plus x or x plus 1.
All right, let's do that. If we do 1 plus x, then we can just write x to the k. We only got 10 minutes left. Let's we only got through the first section, which is actually fine. I'm glad I wrote more than I needed to for today. But let's try to focus on these 4 problems then in our final 10 minutes. Can someone volunteer to try so that we're just not sitting around staring at each other?
Note that what we want is already in the first expression. Like one of the things that we have in our final result.
Yep. Okay. So we got sum from I equals 0 to m of m choose I x to the I times sum from j equals 0 to n of n choose j x to the j. All right, so if we know the degrees of two polynomials, what's the degree of the product? Let's say m plus n, and then we're gonna have k equals 0 down here. Then we're gonna be summing over all solutions of I plus j is equal to k. So that's going to be just m choose I and choose j. Okay, what should I do next?
Well, wait, x to the k, right?
X to the k, you're right, x to the k. Basically, we just want to rewrite this one. We just want to rewrite this one. Let's go back to what we were looking at here. It looks like we're basically almost done, right? We just want to write it in an asymmetric way, going from like I equals 0 to something, right? So we can rewrite this as I equals 0 to k, and then that means that j is equal to k minus I. So this becomes m choose I times n choose k minus I. Okay, and then we had this was a coefficient of x to the k equals 0 to m plus n. We had that this was from before equal to from k equals 0 to m plus n of m plus n choose k x to the k. And so we actually get the Vandermonde convolution just from the same thing, just by comparing coefficients. So the Vandermonde convolution is related to the hockey stick lemma in this instance. So 0 m plus n, m choose I, and choose k minus I. Okay, so I don't want to go on to the calculus review until next time we meet, because we only have 5 minutes left. So here's the exercises that we still have. We have to use a counting argument to prove the hockey stick lemma. We have to use a counting argument to prove the Vandermonde convolution. We have to prove this Pascal sum identity. So let me do an example of the Pascal sum identity. Pascal rectangle sum. So I'll rewrite it here first. So I equals R to M, J equals S to N of I plus J choose I is equal to M plus N plus 2 choose N plus 1 minus R plus N plus 1 choose R minus M plus S plus 1 choose S plus R plus S choose R. So you might be saying, Corbin, how would you even memorize this? Like, why is this useful? What is this telling us? If we draw an example on Pascal's triangle, it will become much clearer. But we're gonna need a bunch of space if it's gonna be a non-trivial example. One, 5, 10, 10.
You can probably guess where the name comes from, given the
15,
hockey stick name.
15, 6, 1. Probably gonna go down one more row after this. 21, 35, 35, 21, 7, 1, 1, 8, 28, 56, 70, 56, 28, 8, 1. And then let's say we have m equal to 4, n equal to 3, r equal to 2, and s equal to 1. Okay, so let's say we have s is, or j is equal to s. So the minimum values, I and j are their minimum values, 2 and 1. So that's 3, choose 1. Sorry, 3, choose 2. So that is this one right here. And then, did I do it? I did it backwards, actually. Sorry. You want to go here. And then we go to 3 and to 4. Okay, so the left-hand side is saying sum up all of these values. Add these up. Okay, so let's add them up just by hand here. So 3 plus 4 plus 6 is 13, plus 5 is 18, plus 10 is 28, plus 10 is 38, plus 15 is 53, plus 20 is 73, plus 35 is 108, I think. So I'm gonna double check, but the sum of this is 108. I'm gonna triple check that.
Yeah, that's correct.
Okay, so now, oh, I need to make one more row. Sorry. So now we have 1, 9, 36. That's going to be 84, 126, 126, 84, 36, 9, and 1. Okay, and so this is saying m plus n plus 2, so that is 9. Choose n plus 1 is 4. So 9 choose 4 is this one right here. So 126 minus r plus n plus 1. So that is 6. Choose r is 2. So 6 choose 2 is
15.
Yeah, 15, but I'm gonna circle that one. And then we have, maybe that should be n plus 1 if I want it to be more symmetrical. But then we have m plus s plus 1 is going to be 6, choose 1 is that one right here. So we have minus 15 minus 6. And then r plus s choose r, that's 3, choose 2, or the same as 3 choose 1. We're going to want that one. So we have plus 3.
Which gives 108. Yeah.
Yep, equals 108. So instead of adding up the 9 numbers, we could have just added up those 4. And so those are like the corner values of the rectangle, you could say. And one thing about this result, when you get to calculus 3, you'll see that this kind of reminds you of some integral formulas where you can know the sum over a whole region just by knowing the sum on the boundary.
That's what I was just thinking, like complex analysis, especially.
Yeah. So this kind of looks like other sums that you see later on in calculus. So this is just an example of it to show you that, yes, it is in fact true, and that it can in fact save you some time and labor. And maybe there are even ways of rewriting it so that it's even easier to memorize and understand what the picture is saying. But so your homework is to do the first 4 problems in these notes. I'll publish corrected versions in a few minutes after this is over. If you have any final questions, I'll take them. Otherwise, you guys are free to go.
Wow, no one thanks me.
Oh yeah, Sam also is helping out too. Yeah. Yeah. So not enough people showed up this time. for me to do what I wanted for the registration stuff. So I guess I'll just harass people about that individually. But yeah, you guys are free to go
Okay, bye.
later.